Okay, well, should we get started?
Yes, yeah, it's just us three
Okay,
so far, but yeah, if you want.
all right. If they're late, it's on them. Um, anyway, welcome everyone to another Call the Doctor. Tonight, I'd like to talk about some ideas I have for improving performance. And this came up dealing with some users who had HDF5 files that were comprised of many, many, many data sets and attributes. And as I'll show, this can lead to not great performance for HSDS. So HSDS was originally targeted at files that contain very large data sets. And the advantage of HSDS, for example, if you are doing a selection of, say, one column of a large, say, two-dimensional data set, that the processing to retrieve all the chunks that intersect with that selection happens server side. And only the actual selection that the user wants comes down the network. So you have one request going to HSDS, a bunch of data IOs happening on the server, and then a small amount of data coming back. And that worked pretty good compared to other solutions for reading, say, S3 data with the H5 library. So let me go on to this. The idea is that we'll reduce number of requests for each action, and that will reduce this kind of piled on latency effect that we see. So here's like two contrived examples. In the first one, I create either an H5 or HSDS file, and then I create a data set that's 1024 by 1024. And then for each of the rows in the data set, I initialize it with some value. So in the HSDS context, we would be doing at least 1024 requests. And each request would be around 4 kilobytes. Now, I think even with H5 you would be told that this is not efficient, that you should instead block up your updates to a smaller number of calls to the library to improve the performance of this. But it's pretty much fine with H5 in the library. But if we're doing this with HSDS and say your latency per request is 0.2 seconds, then you're looking at 3 to 4 seconds to initialize this data set. The second example is, say I want to create 1,000 attributes. So I'm going to have a loop, and for each of these attributes, I'm creating an attribute. And that's a very fast call with the library, but you'll have this minimal lag of around 0.2 seconds, depending upon how distant your server is to these operations. So we could deal with this by adding, say, new methods. For example, experiment with a multi-attribute update that said, here's a bunch of attributes, add these all at the same time. But the problem with that is that you'd have to modify your application to use this. It might be a little bit cumbersome to use the API, and you wouldn't have compatibility anymore with H5. So instead, I'm looking into this technique I'll call pipelining, which I'll explain. So the idea is that rather than every time you do something in the API, you immediately go to the server, we'll have this in-memory data store. We'll call it HDF5 database. And it's a database that can contain all the metadata for a given file in memory, and also recent updates and recent reads of dataset data, right? When the amount of, say, pending updates gets too large, are the user calls a flush command, those pending updates get sent to the server. And we'll be doing some kind of magic so that what would normally be multiple HTTP requests becomes one or a few HTTP requests. The HDF5 by itself doesn't understand file formats. So instead, we have this plugin architecture where you have an abstract interface for readers and writers. So you instantiate this DB, and then you can plug in whatever reader or writer you want. So currently, I have a version of this which has H5Py readers and writers and JSON readers and writers. So for example, if you connect a JSON, let's say you connect a H5Py reader to a database and a JSON writer, you now have the ability to transform HDF5 files to a JSON equivalent, which may or may not be useful, but it's interesting. And basically, we could support any format that kind of roughly maps in to this HDF5 kind of schema, like ZAR, for example. And a follow-on is, oh yeah, there's one idea of the JSON format that I'll talk about later on. So how this works with H5PD. So we'll have a H5PD that talks to the synchronous API of HDF5DB, and it's connected with readers and writers that talk HSDS REST API. Okay, so now in H5PD, you say create an attribute. It goes through the synchronous API to H5DB. That update lives in memory somewhere in the database. And when you do a flush, or when there's too much pending stuff, HDF5DB will tell the writer, hey, writer, I need you to put all this stuff I'm holding in memory into some kind of persistent store. And the writer will have some intelligence to consolidate all these updates to a smaller set of requests to HSDS. And an interesting side effect of this is that in H5PD, we have these utilities, hsload and hsget. So hsload takes an HDF5 file and converts it to HSDS by basically going through each element of the file and calling the equivalent H5Py command. And hsget does the reverse. That code, which now sits in this application in H5PD, can be subsumed by HDF5DB along with the relevant readers and writers. All right. Let me stop there. Any questions? Make sense? Okay, so I've done some experimenting, and I've seen like speedups of 10x for some simple examples. Okay, so we talked about writing. For reading, I would like to do a similar thing, but here, where you are, say, doing a read on a data set for a given selection, there's a trick is you'd like to read ahead and guess what the next read will be, right? So if I'm, say, reading a 2D data set and say the application is reading one row, it might make sense to read the next 10 rows because the cost of that HTTP request will not be any more than reading one row. But now you'll have those next 9 rows in your memory database. And so when the application hopefully goes around and reads the second row, you'll get that basically instantly because it'll just be reading from memory into the code for the client. It's a little bit tricky for multidimensional data sets because you don't know offhand which direction that next selection will go. So it'd be nice to build in some intelligence, try to say like, okay, in call 1, he did this, call 2 did this, call 3 did this. Therefore, I can assume the next call will do a shift in this dimension or with this stride, that sort of thing. So I mentioned plugins. We have the JSON read and writer. We have the H5Pi read and writer. Next up is a REST API. And interestingly, would be a reader and writer that talks directly to, say, the HSDS schema. So now you wouldn't need to have a server necessarily. You could have your client directly writing to the sharded data store of HSDS. So another technique for improving writing will be doing something similar to what ZAR does. It's called consolidated metadata. So if you take the typical HDF5 file and you converted all the metadata to JSON, it's typically not enormous, right? So if it was larger than a couple of megabytes, that would be unusual. So if we can do this for these files, and then on the HSDS side, so HSDS will be getting updates for a particular file, and if no updates have come for that file in, say, 60 seconds, it'll say, okay, no changes are happening right now, so I will create or update the consolidated metadata file for this HSDS domain. Okay, so then that'll be created. That'll live adjunct to the domain in S3 storage. And then when the REST API to read that domain comes, it can download the JSON file as part of that first request accessing the domain. Then in the HDF5 database, we can keep all that metadata in memory. And then anytime a client needs to get the links for a group or read an attribute for a data set, it'll just be in memory and it won't need to go back to the server to fetch that. So in that scenario, the only request that would need to be going to the server would be dataset reads and for data sets that are, say, more than a kilobyte in size. So next steps, I'll be working on cleaning the REST API plugins and then test by downloading HDF5 files and then seeing how the performance compares to what we have now with HSGet and HSLoad. And then look at different pipeline strategies to consolidate multiple updates to one request. On the server side, we'll need some REST API tweaks to improve cases where a request has to come back from the server before the next request goes out. And then the consolidated metadata that I've talked about, and then integrating the H5 JSON package with HSDS and H5PD, which will have the side benefit in that there's a lot of common code that we have for like managing NumPy types that can be in this H5 JSON package. Later on, we can look at the readers and writers that directly talk to the HSDS storage schema. And then it might be interesting to have an H5PD as a layer on top of H5Pi. So then you could be using H5PD to talk to the HDF5 library and read and write normal HDF5 files, but there's some possible value add here. Like we have the PyTables like table class. There's a query API. You can have compressible V-length data sets and possible performance, right? Just like I mentioned, that it's kind of like bad practice to read one element of a data set at a time, but this H5PD layer would hide that extra cost. And then it'd be nice to have a Python implementation for some H5 JSON code. There are a few code paths that have to do like an element by element operations, which is slow in pure Python. So that could be dramatically speeded up by having the Python implementation. That's all I have. All right. Any questions? Okay.
Yeah, just a couple of comments, but if you were going somewhere, please go ahead. Yeah.
No, go ahead, Quincy.
Yeah, no, it sounds very interesting. I like the perhaps future direction where if you're talking to native HDF5 files, you get some added benefits from, you know, the memory database stuff. And I could see a place, and this is super sketchy, right? Because I haven't finished getting my sharded stuff written down well. I could see a place for something like the HSDS pieces of the current HSDS transforming into an accelerator for plain old sharded storage in the cloud, right? Because you're close to S3s, you're already in the cloud, right? You take a huge chunk of latency off the top, and then possibly there's some delegation or, like you say, prefetching and prediction that you can build into the accelerator style version of this. So the client is still more in charge than it is today. But it can delegate certain go fast stuff up into something that's closest to the storage. It won't matter for on-prem probably, but for true cloud, it seems like it would be an interesting kind of synergy. Right.
Okay. Oh, yeah, something else I didn't touch on was this async API. Yep. You know, I've been thinking in the H5Pi community, there hasn't been much interest in the async version of H5Pi, but that's something that I will have in the HDF5 database. So if you are content with using that API directly, that's an option. And if you feel like building an API on top of that, you're also welcome to do that. The HDF5 DB API is pretty simple, and it doesn't have a lot of the convenience aspects that H5Pi has. So like in H5Pi, you can initialize the data set by just specifying the shape and the type, or data and the type, blah, blah, blah. Lots of different ways to do the same thing. Whereas an HDF5 DB API is pretty much, there's this one way to do things, and that's the way you have to do it. So that makes the code simpler. And then the idea of the H5PyD on top of that would add the familiar syntax that we're used to with H5Pi.
Yeah.
So
that would be interesting. Sure.
Yep. All right. Well, if there's no more questions or comments, I guess we'll call it a day for now, and look forward to seeing you guys next time.
All right. Thanks, John.
All right. Bye.